Bharath Rangarajan, who will speak about, well, the fruits of last week talk. It's like kind of a uniform stability for high rank lattices.
I'll start.
Well, you're the expert at my age, believe me. Teach new tricks to old dogs. Okay, Bharath, the stage is yours.
Yeah, hi. So this will be a continuation of last week's talk on uniform stability and asymptotic cohomology. And in this week, we'll actually see an application of the tools that we developed last week to lattices and semisimple groups to show that such lattices are uniformly stable in the way we described it. So since we'll be building on things that we covered last week, I want to spend a little time just revising what we did last week, just to set up all the terminology and the basic ideas quickly. So as we saw, we first defined what an almost homomorphism and closeness to homomorphism is in terms of the defect, which is sort of a local way of thinking about how far it is from being a homomorphism, and the homomorphism distance. So these are two relaxations of homomorphisms, and the question of stability asks whether if the defect is small, then is it close to being a homomorphism? So this was the general definition of what stability was, which we then made a little precise using epsilon deltas, where you say that, okay, for every closeness to homomorphism, is there some small enough defect beyond which it is close to homomorphism? And this is the question of stability. And we also saw that we'll be looking at stability with a linear estimate, where this delta and epsilon are actually connected by just a linear relation. So beyond some small enough epsilon naught, any map with defect epsilon is some constant times epsilon close to a homomorphism. That is the definition of stability with a linear estimate. And we also just revised certain known results, which was that, okay, we always set the family of groups to be unitary groups with a submultiplicative norm, one of which could just be the operator norm. You can just think of the operator norm for now. So we saw that the free group was not stable, amenable groups are stable, and the earlier result, which Andreas showed the week before, was this one. And we also saw where we can somehow, in a toy version, we saw how we can get some connection to bounded cohomology, which is firstly the observation that F2 is not stable and the bounded cohomology is not zero, and amenable groups are stable, and it happens that the bounded cohomology with dual coefficients is always zero. So, and how did this connection come from? Well, you see that if you start with an epsilon homomorphism and you take a log map to linearize it, then what you get actually looks like a 2 cocycle which is bounded. And if you can get that to be a co-boundary, then you can use that as a correction to get a homomorphism, at least in the U1 case. So this is the first connection to cohomology, which is that an epsilon homomorphism, when you linearize it, you do get a bounded cocycle. And if it happens to be a co-boundary, that gives you to get a true homomorphism. And we saw that this works well in the U1 case because everything is abelian. You can just go from U1 to R and you get a true cocycle. But when it's not abelian, then you things don't work out the same way. However, what you do for amenable groups, if you just do it blindly for the non-abelian case of UN, what you notice is that this averaging process, which you could do even here to get a co-boundary, if you do the same thing for UN, which you do for amenable groups, what you get is not a homomorphism, but something which has smaller defect. So you don't go in one step from epsilon to zero defect, which makes it a homomorphism, but you go from epsilon to some epsilon square or something smaller than epsilon. So this is called defect diminishing, which is to say that, okay, let's try to relax this one step of going correction. So you want to correct an almost homomorphism to say that, okay, I don't want to correct it all the way to homomorphism, but another almost homomorphism where the defect reduces asymptotically and the distance is still of the same order as the defect. And we saw that this was sufficient to guarantee stability because you can just keep doing this. At each step, you reduce defect from something to epsilon by 2 and epsilon by 4, ... and this goes to 0 defect. And each time, the distance still goes from epsilon plus epsilon by 2 plus epsilon by 4 plus ... which is like some 2 epsilon. So you see that this slight relaxation of our demands of correction can still give you stability. And the reason we do it this way is because this defect diminishing actually can give you something abelian. What you see is that you can still construct a cohomological theory capturing this defect diminishing with the coefficients being abelian. So, and we to see this in a nicer way, we said, okay, let's work in the case of ultra products, just put it all together. So you combine this whole almost asymptotic homomorphism to get an internal homomorphism, internal map of this kind. And the defect is a hyperreal, which is an infinitesimal. And now we said that when you quotient out all those which are epsilon distance away from the identity, what you get is a true blue homomorphism. And defect diminishing is actually captured by saying, okay, I want to lift this homomorphism to some other map, which becomes a homomorphism when you reduce the defect. So B epsilon is like bounded with respect to epsilon, and I epsilon is like infinitesimal with respect to epsilon. So ideally, you would think, okay, I want to take this all the way up to get a homomorphism even at this level. But defect diminishing is captured by saying, okay, let me not be that ambitious. Let me do it in smaller steps, going from epsilon to something smaller than epsilon. And the advantage is that the kernel of this lifting actually happens to be abelian when the norm you use is submultiplicative. So this hints at an attempt at constructing a cohomology, because now it seems like you're trying to lift a homomorphism with abelian kernel. And we actually also develop this a little more by saying, okay, now we do the same thing as we did for U1 case. We take a log map to go to the Lie algebra now, just like we went from U1 to R through the log. Now you say, okay, you go from UN to the Lie algebra of UN. And now we can do much of the same things that we did earlier, but everything has to be, to maintain this abelian kernel, everything has to be up to infinitesimals. So we started with the log map, and we actually got an action of the group on this B epsilon modulo I epsilon, which happens to be the same as in the log. It happens to be the same as in the Lie algebra. It's like bounded elements modulo infinitesimal elements, and you also had the action of the group on this. And in this framework, if you try to do the same things, you get many of the features of cohomology, just like you got for U1, which is like you take the defect map. This was a defect map. You take the log to get something that looks like this, and this actually looks like a cocycle. Modify modulo infinitesimals, because only then things are abelian. So you get a co-cycle and you want to make this a co-boundary, and this correction by making it a co-boundary this way actually gives you an improvement. This is the defect diminishing part. So you start with the asymptotic homomorphism, construct the defect map, take the log, you get a co-cycle. Now in this setting, if this happens to be a co-boundary modulo infinitesimals, then this correction gives you an improvement, which is what we wanted. This has defect much smaller than epsilon and is order of epsilon close to what you start out with.
Just Bharath, please slightly slower, even for me, which I think I know the material.
No, all of this we
I know that it's a kind of reminder repetition, but somehow.
Since we sort of dealt with it in more detail last week, I thought let's just quickly rehash what we saw. In any case, all of this won't directly impact what we are going to do next. This is just to give you a connection between how this framework was motivated. We'll still redefine the framework in a way that will allow us to work with it further. So far it's just been, how did this cohomology come about? Which is that in defect diminishing, you can still get a cohomology up to infinitesimals. Okay. So now we come to the main part, how you define the cohomology to capture this. So just like the usual cohomology, which you do for bounded cohomology, you say, okay, now you take the internal maps to this W, which was the Lie algebra of the unitary groups. Now you just take the ultra product of these bounded maps at each coordinate. You take the overall bounded elements of that. This is, I'll call this LB. You take the infinitesimal elements of that, which is called Linf. And now you say, okay, I have an action of the ultra power star gamma on this quotient. So W tilde was just W bounded modulo W infinitesimal. So everything happens up to infinitesimal. So you start with something which need not be a true action, but it becomes an action once you restrict yourself to bounded modulo infinitesimals. So it's like how you construct bounded cohomology, but you say, okay, always keep in mind that everything has to be internal, because that's how you get the uniformity, as we saw last week. And then everything you have to do modulo infinitesimals, at which stage things become a little more tractable. So now you have the action of star gamma on this quotient. And this allows you to construct a complex, which again we saw last week. And this complex is a true complex, because now you've quotiented out all the infinitesimals. This is a true action of star gamma. So now you can define the asymptotic cohomology groups of this true complex, because you have already quotiented out the infinitesimals. Everything was up to infinitesimals, but now you have quotiented it out, and now you have a true complex, and this allows you to define the cohomology. And we saw last week that gamma has a defect diminishing if this second cohomology vanishes. Very similar to how we saw that if the second cohomology vanishes for if H2B. Yes?
Your screen share vanished.
Oh shit. Just a second. I'm not sure. Just a second. Okay now? It is a bit of a lag. Okay?
Yes.
Yes.
Great. Sorry for the interruption. I'm not sure what happened. Anyway, so we saw that defining this precisely, we see that if the second cohomology in this framework vanishes, then you do have defect diminishing, as we hinted at. And so now we come to what we want to do now, which is that, okay, so we have defined an entire framework. We have used the defect diminishing to define a cohomology and show that if the H2 vanishes in this cohomology, you have stability. And we also sort of noted that this cohomology looks a lot like bounded cohomology because you do restrict yourself to bounded functions, but up to infinitesimals, and everything has to be internal. So the question is, how similar is it to bounded cohomology? And can we actually do something like we do for bounded cohomology in this cohomology? So before we get to that, let's slightly generalize the definition so far. So far we gave a definition for discrete groups with a very specific set of coefficients, which are the Lie algebras, and that the action on of the group on this Lie algebra came through just the conjugate action, and we defined the cohomology that way. But let's since we want to look at the similarity with bounded cohomology, let's try to sort of generalize or just give a more rigorous framework for how this cohomology is defined. So just like we use the ultra product of the Lie algebras, we can think of any ultra product of some Banach spaces Vn. And we call that an internal Banach space. Internal will always refer to ultra products of something. And you can just think of it as something you do coordinate wise. And we use this ultra product framework so that everything behaves well. You can actually talk about bounded elements, infinitesimal elements. They'll all form subgroups or subspaces and things like that. But for now, you can just formally just think of an internal Banach space as the ultra product of Banach spaces. And we can again define the dual of an internal Banach space coordinate-wise internally. So at each coordinate is the dual of something internal, and we can combine that to get the dual. So V is said to be a dual internal Banach space if it happens to be the dual of something which we fix. So far we haven't done anything beyond just abstract nonsense, just what we did in the classical case where you have a Banach space and you say, okay, it's a dual Banach space. So you're doing the same thing coordinate-wise to define what is an internal Banach space and a dual internal Banach space. Now, next we actually need an action. So for this, the action of the ultra power is not technically an action. It becomes an action only when you restrict to the bounded elements and quotient out the infinitesimals. So we start with an internal map pi. It's an internal isometry at each coordinate. And it induces an action once you restrict to the bounded elements and quotient out the infinitesimals. So such a thing will be called an asymptotic action. So an internal Banach space is just an ultra product, but in everything we do, the group action has to be asymptotic. It has to be an action once you ignore infinitesimals. So this is what we actually got when we were motivating it. We said, okay, you have star gamma and you have a map which is derived through the epsilon representation you got. It becomes an action on the ultra product of the Lie algebras once you quotient out the infinitesimals. So we are trying to replicate the same and generalize it here, which is say, okay, I have a map, an internal map of star gamma, which times this ultra product to the ultra product just to replicate what an action should look like. But it becomes an action only when you quotient out the infinitesimal. So at this level, it is an action. So such a pair, pi, which is internal and an internal Banach space V, is called an asymptotic Banach module. And this is the structure which we use to define an asymptotic cohomology. Okay, right. So now we formalize what we defined earlier, which earlier we did it for the discrete case. Now we are going to do it for the locally compact case. Nothing much changes except that now we say, okay, let this cursive L be the ultra product of the L infinity maps, just like earlier, L infinity weak star maps. And again, you have the bounded elements of this and the infinitesimal elements of this. And again, you can, given this action power of gamma on this V tilde, which was, recall that V tilde is just the bounded modulo V infinitesimals. From this, you can get an action on, it induces an action on this quotient. Again, the same as we did it for the discrete case. And now we have a complex, a true complex, for which we can define the cohomologies. So nothing has changed. It was just like what we did over here.
Just a
Except
moment.
that,
Bharath, you're already in the assuming that gamma is a lattice in G.
no. Right now I'm
So what
just
is gamma?
defining.
So what is gamma in the next in these slides?
So
Slide
as of now, gamma is just a discrete group, which means that we can define things a little simpler. This was just a motivation for how we define the asymptotic cohomology of gamma. Over here, we just say G is some locally compact group and doing the same thing. So far, we haven't defined, we haven't specialized to any group yet.
Yeah, but we go to the where do you define it for G? Like go next slide.
Over here, yeah.
Hold on. Yeah, what is gamma here?
Where is gamma?
You have like in the fourth line, you have the action of gamma star on V tilde. It should be G star.
You're right. It should be G star. You're right.
There's no G.
Yes.
Yeah.
Yeah. So there's no gamma here. So this is just a definition for a general group G. That's it. You're just doing the same thing as before. You're saying, okay, I have some asymptotic action of G on this internal Banach space V. And now I'm using that to construct this complex and taking the cohomology of this complex. This is the asymptotic cohomology of G with coefficients in V. So this is just a definition. I haven't told you what V is, what G is, nothing. You just have some asymptotic action of G on this asymptotic Banach module V, and you can define the cohomology the same way. This is again just a definition.
Maybe a stupid question, but you're all the time saying V is a internal Banach space, but is it even a Banach space, the algebraic ultraproduct of Banach spaces?
It's not. It's technically not. So when we say an internal Banach space, just it's not an internal describing a Banach space. It's an internal Banach space is our definition. It's just the ultra product of Banach spaces.
I see. Thank you.
So I just want to compare this to the definition of bounded cohomology of a locally compact group with coefficients in a dual Banach's module V. So we defined this V was the ultra product. So this is just internal, but we said, okay, this G has some imperfect action of this on V, which means that G has a true action on this. So it has an imperfect action on V and a true action on tilde V, which was up to infinitesimals. And we define the asymptotic cohomology here. The bounded cohomology definition is even simpler. You just don't deal with these internal or asymptotic things. G actually has an action on V, and you define this complex L infinity of G to V, L infinity of G square to V, and these are just G fixed points, G equivariant maps, and define the bounded cohomology to just be the cohomology of this complex. Why I'm highlighting these is just that in many ways they look similar, except for the asymptotics. Because in both cases you restrict to bounded maps, just that over here you also quotient out the infinitesimals, while here there's no problem of infinitesimals at all. And this similarity is actually promising, because now we can say, okay, what if we know groups for which the bounded cohomology vanishes with coefficients in some Banach module V? Can you sort of take some inspiration from that to show that this asymptotic cohomology also vanishes? And if you can, then that immediately gives you stability. And that's the goal of this talk, which is that, okay, we already saw a simple setting of this approach last week, which was that we know that for amenable groups with dual coefficients, bounded cohomology vanishes, and you know that the proof is just averaging the cocycle, keeping so you just average the cocycle, keeping one of the arguments fixed, and to get a coboundary. And we saw that that same method worked even for asymptotic cohomology. You just do the averaging internally, and it still goes through the same way. So the question is, how far can you push this idea? If you know that the bounded cohomology for some class of groups vanishes for sufficiently general set of coefficients, can you do the same thing for asymptotic cohomology? And that's what we want to look at now, which is for certain lattices in semisimple Lie groups. Because this is a classical result of Berger and Monod, which is that, in fact, they show that Hn P of gamma W vanishes for high rank lattices for n up to, I think, the rank of gamma. Rank of gamma -1, I think, I'm not sure. But anyway, that's not relevant to us as much as H2, because H2 is what we are concerned with. Because the cocycles that we get out of this stability problem happen to be in the second cohomology. So we are interested in just the second cohomology. And
the result is for every W, or you need that W is without fixed point?
Well, we will actually give the assumptions that we need very soon. We will, so for the Berger and Monod proof, I think it holds for dual separable W with H2 of gamma, is it gamma? With H2 of G R also being 0. So gamma is a lattice in some semisimple group G. In the Berger Monod proof, you can show that the cohomology vanishes if you assume that H2 of G with no coefficients is 0 for dual separable Banach gamma modules. We'll come to it. We'll come to it very soon. But this is just to say that we have some results for bounded cohomology for lattices and a fairly general set of coefficients. And we want to see how far we can push those proof methods for asymptotic cohomology. Keep in mind that things get a little trickier here because you don't have a true action of the group on the coefficients. You only have it up to asymptotics. And that's where all the subtlety comes in. So before we get to our proof, which I don't know how much we'll actually be able to cover because of these subtleties, let's look at the bounded cohomology proof, because many of the broad ideas, at least the building blocks, the ingredients look similar. and you can get some idea of at least what you might have to do and the difficulties you will face in our cohomology. So let's look at what happens in the bounded cohomology case. So the first thing is, let's get some basic results of bounded cohomology out of the way. So we define the cohomology in terms of a certain complex. So recall that the bounded cohomology was defined in terms of this complex. This itself is not how it's defined traditionally. You define it as a continuous bounded cohomology. So you actually have the complex comprising CB of G to V G to CB of G square to V G. So you have continuous maps. We aren't dealing with that at all. We just define it as L infinity maps. So how are we able to just move between one complex to the other complex and claim that they compute the same cohomology? There's a lot of cohomological algebra and functorial ways of getting through this problem. So once you define the cohomology in terms of one complex, you can play around with these functors and say, okay, you can compute the same cohomology using many other complexes. And one of the general and useful results for bounded cohomology, just keep in mind that right now we are just looking at bounded cohomology. We'll come to ours very soon. One of the general results is that this L infinity of S and V is relatively injective as a G module. So what is S and what is relatively injective? Let me just, so first, relatively injective, just keep in mind that, you know, you have this notion of injective modules, and you have this notion of injective resolutions computing the cohomology in classical cohomology, not bounded. Oh shit, again. Just a second, I don't know why it keeps stopping. I'm really sorry. Yeah. So you have with these injective modules and injective resolutions computing the group cohomology. In the bounded cohomology case, there is another notion, which is a relaxation of that in terms of bounds, called relative injectivity. And once you can show that certain modules are relatively injective and you have a resolution or some complex constructed from that, you can show that they compute the same bounded cohomology as the definition. And so here you say that L infinity of S and V is relatively injective, where S is a Zimmer amenable space for G. And Zimmer amenability is a certain property of the action of G on some space if you have some conditional expectation of this form. Now, you don't need the definition. You don't need to know what it is for now. These are all just things that are classical. All you need to just keep in mind is that to compute the bounded cohomology, even though you have given the definition in terms of something very concrete, you can really play around functorially to compute the same cohomology using various other complexes. And for instance, using Zimmer amenable actions of G on certain spaces. Now, why I'm giving this is because now there are certain classical Zimmer amenable spaces. For instance, if you're given gamma, which is in G, gamma is a lattice in G, then G is Zimmer amenable for gamma. Which means that the cohomology of gamma with coefficients in W can just as well be computed using this complex, which is functions of G. So we defined it in terms of functions of gamma, right? You said, okay, gamma par n W gamma. Now you're using this functorial equivalence. You can say, okay, I know that G is Zimmer amenable for gamma, and therefore you can compute it just as well using this complex. Similarly, you can play around a little more. For G itself, if you have any minimal parabolic, which happens to be amenable in G, you can compute the same cohomology of G with coefficients in any dual V using functions on G modulo P. And you can do the same even for any other closed subgroup of G. You can say, okay, I want to compute the cohomology, bounded cohomology of Q using functions on G modulo P, but with Q equivariant, Q invariance. So this is a general fact of bounded cohomology, which I don't think I can or even will prove, but this all you have to take from this is that you have some freedom in manipulating the complex that you use to compute the cohomology, and that can really help us. So if you have a Zimmer-amenable space, you can construct the same cohomology using a complex built from functions defined on that space. And these all give you examples of Zimmer-amenable actions, which allow you to compute the complex using compute the cohomology using different complexes, which can really help us. For instance, this G mod P will really help us. And where will help us is right now. So the first fact for bounded cohomology was the fact that you can compute the cohomology using different complexes. Just keep that in the back of your head, even just take it on faith. The second thing that you have to take on faith is a certain property of actions of G. So this is called the Mortner lemma. This is another classical fact of G actions on continuous modules. So right now you think of gamma G. Gamma is some lattice in some semisimple group G. So if V is a continuous G module, and if you have two elements, G and H in G, such that G contracts H, that is, you can take conjugates of G to make H go to the identity. So this is what you call contraction. Then if you have an element of V which is fixed by G, then it is also fixed by whatever G contracts. This is called Mortner lemma, and this is again a very classical result. Why do we care about this result is because this really helps with fixed points of V or the action of G, and we'll see how that relates to G modulo P. So again, take on faith the Mortner lemma. You have this result on contraction and fixed points. So what we have is, if G is boundedly generated, so this is a general result. G is boundedly generated by elements contracted by some maximal torus contained in the radical. Okay, this all looks like a lot of words. What you have to keep in mind now is two applications of Mortner lemma, which is that if you take some parabolic subgroup Q of G and take the soluble radical of Q, then if an element of this module V is fixed by this radical, then it's fixed by all of G. The way you get this result is through contractions, but we won't look at the proof of that. All I'm trying to generally tell you a story right now is we are going to use certain facts from bounded cohomology and fixed point results to combine them to get something to show that this vanishes. So the first was just changing the complex used to compute the cohomology. The second is certain results on fixed points. So this is one result, and the second is a certain ergodicity result. Now you already see G modulo P coming into the picture. So am I going too fast? I think I am going too fast. But
It's too fast.
Okay,
It's better to skip a little bit, and what you do a little bit slower, please.
Yeah. So over here, all you need to keep in mind is that we have certain fixed point results that can come to help us. You just have to keep this equation in mind for now. It just so happens to be derived from a certain Mortner lemma, which is about contractions. So just keep in mind that if a vector in the Banach space is fixed by some radical, then it's fixed by all of G. Just keep this in mind. And you can use this to get a certain ergodicity result. And this will be very helpful for us, which is that, so the general ordinary ergodicity result just says that if you have a G invariant map from G modulo P times G modulo P to R, then it is constant. This is again classical ergodicity because this is the Furstenberg boundary of G. Now you can use this and the Mortner lemma that I just discussed to show a similar thing called ergodicity with coefficients, which says that if you have an equivariant map from G modulo P times G modulo P to V, then it is essentially constant. Now, why do we care about this is because once you have this complex, you do get G equivariant maps from G modulo P square to V in the first cohomology, for instance. And this ergodicity with coefficient result says that they are constant, and that's very helpful for us in really simplifying things. So, and this ergodicity with coefficients, it will follow pretty much by using Mortner lemma along with the ordinary ergodicity. Again, this all seems like a lot of things, a lot of overkill for what we want to do, but just keep these two results in mind for now, which is that Vn equals Vg, just as black boxes, for instance. Vn equals Vg, and if you have an equivariant map from G modulo P square or even G modulo P, for instance, then it is constant. Just keep these two facts in mind, and with this, we'll actually show that H bounded at the second cohomology vanishes. Okay, let's begin for the bounded cohomology. Again, this is just a quick, breezy story. So you start with gamma, which is a lattice in G. And to use the fact that it's a lattice in G, the first step you do is to convert the problem to cohomology for G, which is induction. And so you have a very classical Shapiro induction step, which you do, which is you show that H bounded of gamma with coefficients in W is H bounded of G with coefficients in some induction module. This is similar to the usual induction module that you define, but since we want to restrict ourselves to bounded functions, this is L infinity instead of what you would have done L2 in the unitary case. And again, this is classical bounded cohomology. Just keep this in mind that you can go from gamma to something which happens at the level of G. And this coefficients is actually some space that looks like this. You can just convert this to functions on G modulo gamma to W. This is again a very straightforward isomorphism, which we won't get into. The thing is, now we'll say, okay, now we have HB of G with coefficients in V, right? And now we are going to use all the facts that we just hinted at to say that this is zero. Now, what are we going to do? Okay, the first step is what I first mentioned, which is that, okay, I can compute the cohomology of G with coefficients in V using this G modulo P functions, this complex, because G modulo P is Zimmermannable for G. That was the first fact. And now I'm going to say that, okay, I'm not going to treat this cocycle as a cocycle for G, but as a cocycle for Q. This is also allowed because, again, G modulo P is Zimmermannable for Q, as we also already mentioned. Again, another black box that we used. So what I'm saying is, okay, I start with a cocycle at this level for H2, which is omega, which is a cocycle. I'm going to say, okay, take some parabolic subgroup Q and treat it as a Q equivariant function. Now, why you do this is because there's a way of simplifying it a little for Q. Now take the radical of Q. Now you see where the second black box comes in, the Mortner lemma and the Doubler-Gottesky part. I'm getting n equals the radical of Q, which is solvable and hence amenable. Now, omega being a 2 cocycle for Q can be computed using this complex, right? So Q modulo n, because n is solvable and hence amenable. Again, just stop me if I'm going a little fast, but it's mostly a story so far. It's just a broad ideas. Is everyone at least roughly with what I'm trying to do? I want to show that the bounded cohomology of gamma is 0. I took an induction to get G. And now I want to show that the bounded cohomology of G with coefficients in this induced module is 0. Okay, so far?
So V here is the induced module. Can you?
Yeah, V is the
write it
induced
again
module.
explicitly?
Hmm?
Yes. Okay. Thank you.
V is the induced module.
But it's kind of a general treatment now. You see, you look at the cocycle on G, you restrict it to the parabolic subgroup Q. The advantage of doing it is that Q is a unipotent radical, and you can use the fact that cocycles vanish on amenable groups. You see, like we already had the Kashdan results in this language. Well, that Kashdan, like that bounded cohomology is 0 on amenable group. And therefore, you get it that it's kind of induced of Q mod n. In a way, it's a kind of an induction step. You go to a step lower, but it's even better because for the lower step, you just have to look for the trivial module and not for the original module, because you have to go to the fixed point of n, and because of this Mortner lemma, the fixed point of n equal to the fixed point of G. This is a strategy of a Burger Shalom for bounded cohomology. It has nothing to do with asymptotic cohomology.
Yeah. So far, it's just bounded cohomology.
But eventually, the method will try to imitate this in the context of asymptotic cohomology.
So we said that H bounded of G can be computed using maps from L infinity of G modulo P, right? You're doing the same thing for Q here, but the advantage is that the radical of Q is both amenable and normal. This is very helpful. Why? Because firstly, because it's amenable, you can compute the cohomology of Q using this complex. That's okay. That's the same thing as Zimmer amenability that we saw. But it's also normal, which means that if you start with a Q equivariant function of this kind, since it's normal, its image is actually in the fixed points of n. That's very helpful, because now we can use the other Mortner black box to say that Vn equals Vg, which you couldn't do for G, because G, you don't have a normal amenable subgroup that you're looking at. But for parabolic subgroup, you have the radical. So what you're doing is you start with omega, which is a G cocycle, of course, but you're saying, okay, I have limited things to do at the level of G. So let's first simplify it a little by saying, okay, let's treat it as a cocycle for Q, which is a parabolic subgroup. And now you have an amenable normal subgroup of Q. So now if you take omega, this actually has an image in the fixed points of this normal subgroup. But by Mortner, this is actually the same as fixed point of all of G, which is excellent, because now you can think of omega as being reduced to a cocycle of Q with fixed points of V, which effectively becomes a trivial coefficients, because there's no action on the coefficients, right? So that's one of the advantages of dealing with Q. So now if this omega as a cocycle of Q with trivial coefficients happens to be a coboundary, then you can actually do something further. So let's define this as a property, which is you want to write omega as a cocycle for G. You want to write it as omega equals D alpha. This is your overall goal, where alpha is a G equivariant function. Now you're saying, okay, let's try to first do it for Q because it at least simplifies the technique a little. So omega happens to become a bounded cocycle for Q with no coefficients because of this Mortner lemma. Now, if you know that this happens to vanish, then you can actually write omega as D alpha for alpha being a Q equivariant function. It's not what we need, but it's still better than nothing. So this leads to an assumption on G, which we'll use, that H bounded of Q with no coefficients does vanish. In fact, to actually get something from this to G, you need it for two such subgroups. We'll see why, and that'll be the main proof. Suppose G contains two proper parabolic subgroups, Q1 and Q2, such that Q1 and Q2 together generate G. And the for trivial coefficients, the bounded cohomology of Q1 and Q2 vanishes. So this is a property we'll define for G, and this is an assumption on G. Suppose you take this as an assumption on G, then what can you do? So we started with omega, and we said, okay, we treat it as a cocycle for Q. We can treat it as a cocycle for Q1 and as a cocycle for Q2. Now, the fact that H2 bounded of Q1 with trivial coefficients vanishes means that this is actually D alpha 1 for Q1 and this is actually D alpha 2 for Q2. Okay, so far so good. What can we do with that? This is what I just said. We start with omega for G, treat it as cocycles for Q1 and Q2 and say, okay, now assuming that with trivial coefficients for Q1 and Q2, the cohomology vanishes, we can actually write omega as D alpha 1 for Q equivariant and D alpha 2 for Q2 equivariant. How does that help us? Well, now you have a cocycle, one cocycle for Q1 intersection Q2. You're just saying omega is D alpha 1 equals D alpha 2, which means that D of alpha 1 minus alpha 2 is 0. So this has no co-boundary, but it is Q1 intersection Q2 equivariant, right? You start with alpha 1, which is Q1 equivariant, alpha 2, which is Q2 equivariant, then the difference is Q1 intersection Q2 equivariant, and D of that is 0 because both of these are omega. So what we have is, we start with omega, and we get something like alpha 1 minus alpha 2, which is a one cocycle for Q1 intersection Q2, or rather P, because P is contained in Q1 intersection Q2. Why does this help us? Because H1 bounded is always 0. That's very helpful. This is one of the basic bounded cohomology results, which is that H1 bounded, it has to do with, affine actions with bounded orbits. It's 0. Just again, take that as a black box. So you have alpha 1 minus alpha 2, which happens to be D beta for a P equivariant function beta at the level of 0. Right? So you start with omega, which is at the level of H2 of GV, and we get alpha 1 minus alpha 2, which is H1 of P. And we say that this is anyway 0. So you write alpha 1 minus alpha 2 as a co-boundary of some beta, which is P equivariant. But this is very close to finishing up, because if you have a P equivariant function from G modulo P, through a very simple elementary transformation, you can construct a G equivariant function on G modulo P times G modulo P to V. This is just the way you construct it. This is just a simple, quick exercise to check that this is G equivariant. Now we come back to the ergodicity result, which says that a G equivariant function from G modulo P times G modulo P to V is constant. which means that this beta hat which you constructed is constant, which means that beta is also constant, which means that d beta is 0. What does that mean? That means that alpha 1 equals alpha 2, because this was equal to d beta. So you have omega, which is written as d alpha 1, which is both q1 and q2 equivariant. But by the property which we defined, q1 union q2 generates G. So alpha is G equivariant. That was very fast, but let me recap what we did. We said, okay, let's start with omega over here and treat it as a cocycle for some parabolic subgroup Q. The advantage being that this parabolic subgroup has a radical which is both amenable and normal. The amenable part can be used to sort of give another complex computing the cohomology. So omega can be put in this complex. The normal part can be used to get the image of this Q equivariant function in the n fixed points. But the n fixed points are the same as g fixed points by Mortner, which reduces the problem to no coefficients at all or trivial coefficients because there's no action Pg. So now if you make some assumption on H2 of Q with no coefficients vanishing, then you can actually say something about omega being d alpha for some alpha, where alpha is not G equivariant, but at least Q equivariant. That's what you do here, but you do it for two subgroups because you want to use those you want to play those against each other to get it for all of G. So you say, okay, you do the same thing for two subgroups, Q1 and Q2. Suppose G has two such subgroups such that they generate G and the cohomology with trivial coefficients vanishes. Then you can write omega as d alpha 1 and d alpha 2 for Q1 and Q2 equivariant maps, giving you a one cocycle for Q1 intersection Q2, which is P equivariant because P is contained here. And now you use the fact that H1 anyway vanishes to get this as a coboundary d beta, which is P equivariant function on just G modulo P, which can be used to construct a G equivariant function on G modulo P times G modulo P, which has to be constant because of the ergodicity property we mentioned, which makes d beta 0, which means that alpha 1 equals alpha 2, which means that alpha 1 and alpha 2 are both Q1 union Q2 equivariant, but since they generate G, it's G equivariant. This is the rough sketch of the proof of the vanishing of bounded cohomology of gamma, at least for degree 2. All of this works only in degree 2 because you don't have this ergodicity result for higher degrees. For instance, we don't have G modulo P times V, G equivariant being constant. If you had that, then our life would have been very simple because the cocycle omega you start with would have actually lie here, and you can just say that that is constant and just make it vanish. It only works at the level of 1 and 2, the ergodicity property. So this is the proof of Monod and Shalom. Actually, it's not exactly the proof. This is an adaptation of that proof to capture the techniques that we try to implement for H8. This is the kind of proof that you want to do for H8. So far all along we did it for bounded cohomology. How much can you stretch this sort of method for H8, which is the asymptotic cohomology? That's what we'll sketch so far. So any questions so far? I apologize for making it very quick, but it's subtle and there are many details, but I at least want to convey the broad ideas as much as possible, which is an induction step and then trying to simplify the problem by dealing with some parabolic subgroups and reducing the problem to it vanishing for those parabolic subgroups using the assumption, and playing two parabolic subgroups against each other to get it for all of G. That's the broad idea. And that's what we want to implement even for HA, which is our asymptotic cohomology, where things get much more subtle. The first step is, do you still have these functorial machinery to transfer between different complexes computing the same cohomology? Luckily, we do. And again, the proof is, a lot of abstract nonsense. You again start with some Zimmer-amenable space S, and you can compute the cohomology of G with coefficients in V using functions on S, just like you did for the bounded cohomology. This is just manipulation. Since there isn't much to do at the coefficient level, you can just deal nicely with just the arguments and then combine it functorially. Again, this is abstract nonsense, just like bounded cohomology, which is good for us because at least we have a start. We say that, okay, just like you did for bounded cohomology, you have different complexes computing the cohomology. You can do the same thing over here.
Do you have S is just G mod P, right? Or you have another example in mind?
It's G mod P, but we also try to say, okay, you can compute HA of gamma in terms of L infinity of G. It's the same three examples that we did over here. So you recall that over here we use this overkill of Zimmer amenability to get some examples of other complexes used to compute the same cohomology, right? For instance, computing the cohomology of gamma with coefficients on V, you could do it using functions on G because G was Zimmer amenable for gamma. You do the same thing for minimal parabolic using the Furstenberg boundary. G mod P is Zimmer amenable for G. It's the same three examples that we're going to use. So the point is, using that same abstract methods just functorially, you can get other complexes computing HA, just like you did for HB. There isn't much very different over there. See, for gamma in G, you can compute it using just G, for instance. S could just be G. And again, for P being a minimal parabolic in G, you can use G mod P. And same for any closed subgroup Q, you can again use G mod P. Just the same. This is just the same sort of method. And even induction can be very carefully done internally. Just do it at each coordinate wise to get some induced module such that HA of gamma with coefficients in this internal Banach space is the same as HA of G with coefficients in some other internal Banach space, the induced module. Again, this also can be done carefully internally, making sure of the asymptotics, not a problem. The main difficulty comes in the Mortner lemma and the ergodicity part. So we have V, which is some module. Do we know? So in the classical case, we said that Vn was equal to Vg. And what was hiding over there was that the action of G on V was continuous. That's how, because as I mentioned, we needed this contraction lemma, right? We said G contracts H if this goes to the identity. And for this, we need the continuity to go from that to this, which we don't really have here because it's all L infinity modules and you quotient out the infinitesimals. So that's not very easy to do over here. So the question is, do we have the Mortner lemma over here? Do we have some analogous statement? We have Vn equals Vg in the bounded case. In the asymptotic case, do we have tilde V up to infinitesimals? Is it true that those which are fixed by N are also fixed by G? And do we also get this ergodicity result, which is that if you have functions from G mod P squared to V, which are G equivariant up to infinitesimals, are they essentially constant? Here also we have a problem because we need the separability in the classical case to reduce the ordinary, the ergodicity of coefficients to ordinary ergodicity. So these are the two main technical subtleties. And again, I don't have time to get into it, but this is the main hard part of the paper, which we spent a lot of time on, because the continuity part of the action is not available to us at the asymptotic level. So we need to do a lot of fixes. We need to make the action true. So over here we have star G like very roughly acting on the internal space. It's an action only modulo infinitesimals. So we need to correct it to a true action which is continuous, at least on some subgroups, and then apply the classical thing internally. So again, that's a whole other story which I certainly don't have time for. But the good news is that after a lot of difficulty, it is true. So we can prove the Mortner lemma and the ergodicity part also in the asymptotic setting with a lot more difficulty, with a lot more subtle machinery which you use. It's not as simple as in what we do for the bounded case. Okay, so again, taking these two as black boxes as we took in the bounded case, we can combine all those results to do the same thing as we did in the bounded case. We start with omega, which is cocycle for G. We take some parabolic subgroup Q so that it has an amenable and normal subgroup, which allows us to reduce the problem to ordinary, to asymptotic cohomology of Q with no coefficients, trivial coefficients. But over here, to show that this omega can actually be written as d alpha for alpha being Q equivariant, we want HA of Q with trivial coefficients to be 0. And this involves not just HB being 0, but another additional assumption. That is, if, with no coefficients, what we see is that if H3 of Q is sort of closed, or rather it's called Hausdorff, and H2 of Q is 0, then this together implies what we need here. In the bounded case, we just need H2 bounded of Q with coefficients in R was 0. Here, analogously, we need HA of Q with coefficients in the hyperreals is 0, and that is implied by two simpler conditions on the bounded cohomology, but at the level of H3 and H2. So now once you have all of those conditions, which we call, just like over there, we had two such subgroups, we ask for the same thing here. We have Q1 and Q2, both contain P, together generate G. The second bounded cohomology vanishes. The third bounded cohomology, a Hausdorff, and these two together imply HA2 of Q hyperreals vanishes. This is again the analog in the asymptotic of the bounded method that we used. Once you have this assumption on G, then pretty much combining the Mortner lemma, the ergodicity part, and this assumption, you do the same thing as you do for bounded cohomology to get H2 of G with coefficients and V vanishes. This is so the real difficulty is in plugging in those black boxes that I mentioned, which was the Mortner lemma and ergodicity for the asymptotic situation, and the assumptions on G, which is so far I've given you, or at least hinted at a proof of the vanishing of the cohomology for certain gamma and certain G with this property.
Bharath, maybe you can say a few more sentences how H3 of the bounded cohomology comes to the game, because that's somehow was not clear. You know, in the classical bounded cohomology, it does not appear. So
yeah, okay. Yeah,
explain why
that's
it's radically
not
opposed.
actually very hard to see, because okay, let's say you want HA2 of Q with coefficients in R. What does this look like? This is there's no action of Q on the hyperreals here. It's a trivial coefficients, right? So if you take some omega, which is here, if you have some cocycle here, you can actually, what it looks like is d omega is close to 0. That is, d omega is in H3 bound. So, okay, how can you see this directly? What does this omega look like? It's a sequence of true cocycles at the level of ultra product. Each of these omega n is actually some function of q times q times q times q to r. No, it's just 3 q's, right? Such that d omega n is infinitesimal, which means that d omega n goes to 0. What I'm saying is things become much simpler because now you have no action. So this actually just decomposes as an ultra product of true cocycles. So if you start with a cocycle at the level of asymptotic cohomology, what you get is this is, if you just write it out internally, you get d omega n actually goes to 0. Because what you say, d omega tilde was 0. That's what it means, that it is an asymptotic cocycle, right? Which means that d omega n actually goes to 0 if you write it out internally. So if you know that this d omega n can be written as some d something else, alpha n, then omega n minus alpha n is a true 2 cocycle. So an asymptotic cocycle with trivial coefficients can be thought of as some sequence of 3 cocycles where the boundary map goes to 0. So you first correct it at the level of H3 to get a true cocycle at the level of H2. And then you assume that H2 is also 0 to correct that to a coboundary at the level of H2. That's how you get H3 here, because you actually have coefficients in the trivial modules, and this asymptotics means that this is not a true 2 cocycle, but something that becomes a cocycle only modulo infinitesimals, which means that it's actually a cocycle at the level of H3, which you first want to correct it at the level of H3. So you don't even need Hausdorff here. If you make a stronger assumption that H3 bounded of QR equals 0, then what you're doing is you're first correcting it at the level of H3 to get a true cocycle at the level of H2, and then correcting it at the level of H2. So together, this will imply that H2Q with coefficients in the star R is 0. At least this is how you get H3 here. Because to show that H2Q with trivial coefficients asymptotically is 0, you have to involve H3 and correct it there to get a true cocycle and then come back. At least this is morally why you get H3 also as part of the assumption here, even though in the bounded case you only had an assumption on H2. Okay, so for all of these stories, since I don't have much time left, I'll just tell you that, okay, we seem to have some sort of a strong assumption on what the groups G are. We need 2 parabolic subgroups which together generate G, and that bounded cohomology with trivial coefficients at the level of H2 and H3 have some conditions. Luckily, that's not so restrictive a property, and we show that there's a pretty nice class of groups which all have this property, which is If you think of non-Archimedean fields, then pretty much all of the groups that you're interested in have this property. If you're, and the same holds for complex Lie groups, all of them have this property. Great. The level of real Lie groups, you have to be a little more careful. You have to analyze when all you can find two parabolic subgroups with vanishing trivial cohomology at the bounded level, and you still have a reasonable set of types of Lie groups which have this property. So all of this is analyzed in our paper, which will hopefully be out on arXiv in a few days. And yeah, so that's pretty much what I wanted to talk about. But this raises some questions, which is firstly, whether you need this property GQ1, Q2, or is it just an artifact of our proof method? Because in Monod-Shalom's proof, you have some more nice functorial ways of working with bounded cohomology, and they don't use such a strong property of Q1 and Q2. They just say, let's assume that H2 bounded of G with coefficients in R vanishes. So the question is, do we need this property GQ1, Q2? That's the first thing. Second thing is, do we need to do all of this at all? That is, can you just work directly at the level of bounded cohomology? That is another question which wasn't very clear to us. And more open-ended questions are, how can you model uniform stability using cohomology but without linear estimate? So all along we use linear estimate because once you have this defect diminishing step, you immediately are forced to get linear estimate. So if you say, okay, maybe not all my groups need to be stable with the linear estimate, can you still do something? You still have some abelian kernel lifting. Again, that's a very broad open question, and a very interesting question which might have further applications to Sophic or hyperlinear groups, for instance, is what do you do if the norms are submultiplicative? Because this abelianness of this defect diminishing part all needed the submultiplicativeness. So you can ask, what if the norms, for instance, the normalized Hilbert-Schmidt norm, or the norm on the normalized Hamming norm on symmetric groups, there are defined Sophic and hyperlinear groups. Can you still have some sort of techniques to reduce the defect when it's not submultiplicative? So these are some very broad, and frankly, I've thought about some of them and they were pretty hard. So, but it might be worth looking at if you're interested. I'll always be happy to discuss more. Many of the subtle details that I very quickly skimmed through, but I think I'll